In this video we're going to look at annotation options that help understand samples in terms of quantification. The annotation has a set of options that relate to tables. So this is a quantification table that is generated using the quantification option, and these can be generated from regions and components, or you can have regions and components taken from the active tile only. So in this case, this quantification table is taken from the VAMAS block that is displayed in the active tile. In addition, we have new options on the text property page, and these include a tick box that says display live formula from quantification table. So the same options that are available on the quantification property page are also available in a different form, where we can generate a formula that is calculated from quantification regions. I've got a set of regions defined on each of these copper peaks, and I'm generating a table that is purely based on the information that is being gathered from these copper peaks. So I'm looking at the proportion of copper as reported from each one of these quantification regions. The results here are demonstrating that there's work yet to be done to establish the correct quantification for these data. However, I have another example here where the quantification has been performed in terms of Scofield cross-sections and also an escape depth correction, and then two formulae have been displayed over the data. The first one is just an example of what we're expecting to find, so this is a pure text-based formula, and this second one here is calculated from regions and components that have been defined on these data. So for example here we've got a pair of component peaks representing different carbon signal, and within the oxygen I have a pair of peaks here that are representative of signal that we assume is coming from a carbonate and some OH terms. So combining the information of regions and components allows us to display this live annotation text that is representative of the quantification that we're getting from these data. Quantification for these data has been achieved by correcting the peak intensities for Scofield cross-sections corrected for escape depth. The importance of escape depth can be demonstrated if we look at the sample where we had regions set up and quantification based on copper peaks. Now this is not a normal quantification. This is simply to demonstrate that the correction factors that we're applying to these photoemission peaks are consistent. So a set of regions are set up, low kinetic energy copper peaks here, high kinetic energy copper peaks here. The higher kinetic energy peaks are able to generate more electrons than you would expect relative to the lower kinetic energy because of the solid state properties of the material. And this is the function of the escape depth correction. We need to modify the Scofield cross-sections to allow for the fact that the sample will attenuate signal depending on the kinetic energy of the electrons leaving the surface. So at present we've got none is the correction for the escape depth, and we're going to switch to the effective attenuation length. And when we press OK, we see the Scofield cross-sections that have been corrected for the escape depth are now returning a reasonably consistent answer from each one of these copper peaks. This demonstrates that we can quantify using any of these photoemission peaks. They will give reasonably comparable results. The choice of the photoemission peak then would be the one with the greatest signal, so we get the best signal to noise. As a further example of how escape depth is of importance when quantification, we can look at a magnesium sample and compare the amount of magnesium reported by the 1s compared to the 2s and 2p, and you can see that the energy for these peaks are very different. Let's first put up some annotation that is based on this quantification table as a formula. and we'll take the data as being live, so this means it's going to be gathered from the quantification regions, and we'll use the active VAMAS block, and I say apply, and as a consequence we end up with a string that is constructed from the quantification table that gives us an indication of how much we have of each one of these photoemission lines. Let me just change the font. So I'll go to the history, I'll select, and we'll go to 48 and apply. Here we have the formula, and you can see that it's underreporting the amount of magnesium if we'd use the 1s compared to the 2s or the 2p. So let's now do the correction again. And we believe this to be a bulk material, so the effective attenuation length is appropriate, and I'm selecting this, apply, and once again we end up with a reasonable quantification if we apply an escape depth correction in addition to these Scofield cross sections. One of the advantages of having traceable quantification is that when you look at a different sample and you apply the same quantification procedure, that is to say Scofield cross sections corrected for escape depth, and you get a different result as we do here, then we have to ask questions about why the signal for this magnesium 1s should be more intense than we would expect for the magnesium 2s and 2p. One reason might be the instrument is somehow amplifying signal at low kinetic energy for this magnesium 1s, or the other reason might be within the sample, that if we had a thin film of magnesium, then you would expect a bulk correction to amplify the amount of magnesium. So you can ask questions about the instrument, and you can ask questions about the sample itself to try and better understand the analysis of these XPS data.